Assalamu alaikum dear viewers, Shoaib Ahmed is here with a new lecture of the electrical machine subject, and today we are going to discuss the short circuit test in a transformer. And already this topic is covered in our laboratory series of the electrical machine subject, and you can find out this experiment short circuit test of the transformer from my YouTube channel playlist Electrical Machines Lab, where you can find out the short circuit test of the transformer which is performed already on the YL195 trainer. That you will find out the experimental analysis through the electrical machines video series lab on my playlist. Okay, so now we are going to discuss the theoretically aspect of that short circuit test of the transformer. The short circuit test of the transformer is used to measure the copper losses in the transformer. In the previous lecture, we have done or covered the topic of the open circuit test of the transformer. That in the open circuit test of the transformer, that test is used to measure the iron losses or core losses in the transformer, and the copper losses in the transformer that are in the electrical machines, that we can easily find out through the short circuit test, or which is normally called the impedance test of the transformer. And the copper losses are totally depend upon the ohmic resistance of the which are produced in the windings of the transformer. Okay, so this test is used to determine conducted to determine the RO1, RO2, XO1, XO2 and full load copper losses of the transformer. If you find out the impedance in the transformer, then we need to require the values and you find out the values of that resistance and the reactance component in the transformer. Then we can easily find out the impedance, because impedance is the sum of all the resistive and the reactance component in the transformer. Okay, so see, this is the circuit diagram of the short circuit test of the transformer. Okay, so in this test, if you can see the main circuit diagram of the transformer, is that the high voltage winding of the transformer or the main transformer is connected with the V1 supply, okay, variable V1 supply, and low voltage winding is shorted or short circuited by the thick conductor, Now here we are using the variable auto transformer to vary the amount of the voltage, and that voltage can be measured by the voltmeter and the input power. Okay, so that will be measured by the wattmeter, and ammeter will give us the current which is to be flowing from the primary winding, I1 current which is flowing in the primary winding of the transformer. So while making short circuit test, okay, low voltage winding is always short circuited. As you can see from the diagram, the high voltage winding is connected with the variable AC supply voltage, and low voltage winding is it's short circuited by the thick conductor, and measurements are made on the HV winding. Means from this diagram you can see all the metering instruments that are to be connected with the HV winding of the transformer, and LV winding is the short circuited. Why? See this example from the mathematical expression, that if just I'm giving you the theoretical idea, that if we are measuring the parameters on the HV winding of the transformer, then what happened? It means if we are measuring the all the measurements are to be taken on the LV winding. Of course, HV winding is short circuited. Means if we are connecting all the measurements or all the equipment metering instruments on the LV side, and HV we are going to short circuit, what happened? The voltage is inconveniently low. Voltage is inconveniently low, and current which is on the your low voltage side will be inconveniently high, because according to the transformer relationship, the voltage and currents are inversely proportional to each other. So consider this the case of the HV side and LV side, that if we have a transformer of the P is equal to 200 kVA, and voltage we are given to the transformer is that we have a 2200 volts transformer. Means this is the E1, okay, and this is the E2. So means this 2000 voltage is the high voltage winding side, and this 200 voltage is the low voltage winding side. So find out the current on the both cases, on the LV side and on the HV side. So what is the formula for calculating the current? I is equal to P over V. Here power is that 20,000, okay, 200 multiplied by 100, okay, and then you can find out, this one is the, kilo, okay, and you can find out that 100 ampere, and here it is a 1000 ampere, okay. So you can find out that I is equal to P over V, so 200, okay, and multiplied by kilo, 1000 divided by 2000, okay. By simplification, you can find out that this will be like 3, 0 will be cancelled out, 2 and 2, and you can find out that 100 ampere, okay, from this expression. Means I is equal to that 100 ampere. Now coming towards this, we have the same here on the HV side case, we have put the value of the 2000 volts instead of the low voltage side. We are putting the value of the HV voltage. On the low voltage side, take all the parameter kept constant, but LV side we are going to take here I is equal to P over V. We have a P 200 multiplied by 1000, okay, divided by, we have a low voltage side is the 200 volt. So here we can find out that 2 0 are being cancelled out, and we will find out the 1000 ampere. Means if we are connecting the metering instruments on the LV side, then it will be the 1000 ampere current, okay, and if we have a HV side, if all the measurements are to be taken, then we have calculated the current, which is the I is equal to 100 ampere. So from this expression is that if we are taking all the measurements on the HV side, or for example on the LV side, then voltage is inconveniently low, but current is inconveniently high, so it is very difficult to measure these amount of the currents in the real in the practical application. So we have to keep all the measurements, taken all the measurements on the HV side, because 100 ampere, or for example this is the normal case that we are taking that 100 ampere, so current is very low, and that can be easily detected or to be measured by the instruments which are to be connected with the HV winding of the transformer. Okay, now see these points. The low input voltage is gradually raised at the voltage VSC. Full load current I1 is to be flowing from the transformer. As you can see from the diagram, this is the variable auto transformer that is connected with the supply. We are gradually increasing the applied voltage, supply voltage on the transformer. What happened? That at which current I1 is to be, full load current is to be flowing from the transformer until that voltage that reach at the VSC short circuit. Okay, so at that VSC is to be reached, then what happened? I1 current is to be flowing from the transformer, which is the full load current, and that current represents the copper losses in the transformer. So there is no output from the transformer under the short circuited condition, as you can see from this diagram. Okay, the secondary side, which is the low voltage winding, there is no any output or no any load which is connected with the transformer. Only that winding is the short circuited or shorted with the help of that thick conductor. Therefore, input power is all loss, and this loss is almost entirely the copper loss. That loss means when the VSC is until raised, when we are given the applied voltage, AC supply voltage to the primary winding of the transformer, then when I1 is to be flowing, when the VSC is gradually reached up to that VSC voltage, V1 is reached up to that VSC voltage, then full load current is to be flowing from the transformer. That full load current represents the copper losses in the transformer. Okay, so it is because the iron losses in the core of the transformer is negligibly small, because we are conducting this means VSC is to be applied voltage, okay, that at which the I1 current is flowing, which is very low one. So copper iron losses or the iron losses or the core losses are negligible in this case, and I1, which is the short circuit current which is flowing from the transformer, so that will be the your copper loss. Okay, and then small voltage, which is the VSC, is very small, because 5 to 10% of that applied voltage we are given to that primary winding of HV winding of the transformer, then full load current will start flowing from the transformer. Hence wattmeter will practically register full load losses, copper losses in the transformer winding. Okay. Now see the parameters. Full load copper loss. Okay. So this will be the input power in terms of the copper losses. Applied voltage we are given, which is to be read by or measured by the VSC. Okay, that will be read by the voltmeter. Full load primary current is the ammeter, which is connected with the transformer, is that I1. So copper loss will be your I1 square RO1. Okay, P is equal to I1 square RO1. Okay, so where RO1 is the total resistance of the transformer referred to that primary. This is the RO1 is the transformer resistance that referred to that primary side. So total impedance referred to the secondary side means if we have find out the impedance in the transformer, then total impedance referred to this primary side, that will be the ZO1. So it will be division of that VSC divided by I1. Z is equal to V over I, and here we are taking the VSC, okay, and I1. VSC is that value of the voltage where until reach up to that VSC value, if we applied voltage is reach up to that VSC value, okay, if we are gradually increase the value, then I1 current is to be flowing from the transformer. So impedance, okay, we are find out that VSC divided by I1. So total leakage reactance referred to the primary. Total leakage reactance referred to the primary is that XO1. Here means ZO1 is equal to RO1 square plus XO1 square. From here you can find out the XO1 value. So XO1 is equal to ZO1 minus RO1 under root that whole square. Okay. So short circuit power factor. That short circuit power factor can be measured, that cosine phi s is equal to power divided by your wattmeter that gives us the voltage, that gives us the rating of the power, divided by VSC I1. You can find out the power factor of that in the short circuit test of the transformer. So the short circuit test gives the full load copper loss, RO1 and XO1 components in the transformer. So if we can summarize this lecture, then we have concluded that the short circuit test is used to find out the copper losses in the transformer. As you can see from the diagram, the HV winding of the transformer is connected with the supply side AC supply voltage, and LV winding of the transformer is kept shorted or short circuited with the help of the thick conductor. And HV winding, all the readings are the instruments which are to be connected with the HV winding of the transformer is to be all the measurement parameters are to be taken or measured with from the HV side, and LV side we have shorted. If we have connected all these equipments or instruments, measurements are to be taken on the LV side, then voltage will be inconveniently low and current will be inconveniently high, which is very difficult to measure the amount of the currents with the help of the such type of the instruments which are connected with the transformer winding, okay, LV winding. So we have performed this test on the HV winding, and LV winding is to be short circuited with the help of the thick conductor, okay, and we have applied the voltage and VSC. When applied voltage is given to the HV winding of the transformer is gradually increased, reached up to that VSC, then I1 current is to start flowing from the transformer, and that will be called as the copper losses, and this type of the test is used to measure the copper losses in the transformer. So thus this test will give us the readings of that XO1 impedance, reactance, and your resistive factor, and also the copper losses, and you can also find out the impedance from these parameters, because impedance is the sum of all the resistance and the reactance component in the transformer. So dear viewers, this was the today's lecture regarding the short circuit test of the transformer. I hope that you have understood today's lecture, and at last, please don't forget to subscribe my YouTube channel. Please like my videos, share my videos, and subscribe my channel. Please press the subscribe button, hit the bell icon button for more informative videos related to the electrical engineering area. Thank you.